Welcome to the Whispering Scientist. Tonight we begin a journey exploring the most profound extremes ever attempted by the human spirit, the gentle, terrifying facts of space travel. The moment we leave the blue cradle of Earth, everything familiar disappears. There is no air, no ground, no sound, and no warmth. Yet, it is within this absolute void that we build fragile, beautiful sanctuaries, allowing the human body to persist where biology itself should fail. For now, all you need to do is relax. Let your mind soften and your breathing slow, and allow yourself to float gently into rest as we explore these quiet truths. Our first sanctuary is not a massive station, but a small, flexible vessel, the spacesuit, a tiny personal spaceship built for one. To consider it mere clothing is to miss the miracle of its purpose. It is an independent, one-person spacecraft, meticulously crafted to keep a fragile human alive in a realm that offers every possible threat to existence. Out there is no air to breathe, no pressure to hold the body together, and temperatures that can swing hundreds of degrees in mere minutes as an astronaut moves between the sun's blazing light and the deep, immediate shadow of the void. Every layer of this portable world serves a critical, non-negotiable purpose, woven together in a complex tapestry of survival. Deep inside, closest to the skin, an inner lining wicks away moisture and sweat, managing the body's own atmosphere. Encasing this is the pressure garment, a tight, multi-layered cushion of fabric that gently yet firmly hugs the entire body. This internal pressure is paramount. Without it, in the vacuum of space, the very fluids within our blood and tissues would begin to boil and turn to gas. The outer shell, the last defense, is a protective layer designed to withstand the universe's silent threats, razor-sharp dust motes that float without friction, and tiny high-speed meteoroids traveling faster than any bullet. These particles, no larger than a grain of sand, could punch a hole through metal, but the suit's engineered layering works to break them up and absorb their energy before they reach the fragile skin beneath. Perhaps the most iconic piece is the helmet visor, a window to the infinite night, which holds an unexpected secret. Embedded within its surface is a thin layer of real gold. This gold is not for decoration, but for life itself. It acts as a silent, unmoving shield, reflecting the harsh infrared and ultraviolet light of the unfiltered sun. From Earth, the sun is a soft, gentle yellow diffused by our forgiving atmosphere, but in space it is a fierce, blinding white sphere, casting sharp, absolute shadows. The gold ensures the astronaut's vision is not instantly scorched by this raw glare, a constant reminder of the violence inherent in starlight. When Earth's shielding is gone, the life support system is carried in a backpack, a meticulously engineered unit that is the very heart of the suit's artificial world. Within it are the sealed oxygen tanks, the quiet fans, and the carbon dioxide removal system, which cleanses every exhaled breath before recirculating it. Cooling tubes, thinner than thread, are woven throughout the suit, carrying circulating water to regulate the astronaut's temperature, managing the intense heat generated by both the sun and the body's own exertion. A single unseen tear in the fabric could initiate a catastrophic failure, a leak that would drain the precious air into the vacuum. This means every seam is inspected, every stitch verified, and every connection tested again and again, long before the airlock door opens. On Earth, a fully equipped spacesuit can weigh over 100 kilograms, an unbearable, crushing load that requires cranes and harnesses for training. Yet, in the silent freedom of orbit, this tremendous weight vanishes entirely. The suit floats just as its wearer does, a buoyant, gentle cocoon. This contrast highlights the immense technological burden we carry just to survive outside our natural environment. The weight is there, but its force is only felt in the arduous training simulations deep underwater on Earth, preparing muscles for a world of deliberate, tethered movement. When an astronaut prepares to leave the shelter of the spacecraft or the International Space Station, they commit their very existence to this portable world. They must trust that the tiny bubble of air and pressure, the thin shell of metal and fabric, will hold against the total emptiness of the void. The suit is a commitment, a final act of engineering confidence, a miniature piece of the Earth carried out into the silence of the infinite night. To step outside is to step into a silent alien ocean, protected only by this complex, multi-layered sanctuary, a testament to the fragile persistence of human life in the most extreme environment we know. As we drift deeper into the quiet mechanics of orbital life, we encounter a fascinating, often uncomfortable truth. The human body, so perfectly sculpted by millennia of evolution under Earth's constant, gentle pull, is fundamentally misplaced in microgravity. Our next journey explores how the simple absence of weight reshapes the very framework of our being. Beginning with the spine itself, imagine a sudden, slow relief, a feeling of uncoiling that stretches through the core of your body. In the absence of gravity, the spine, which on Earth is constantly compressed by the weight of the head and torso, experiences a liberation. The tiny filled discs and soft cartilage between the vertebrae, which act as shock absorbers, are no longer held down. They gently separate, allowing the spine to elongate, resulting in astronauts temporarily growing taller, sometimes by as much as several centimeters. This physical phenomenon, known as spinal unloading, can feel incredible at first, like a long, deep stretch after a lifetime spent hunching over or standing upright. It is a slow, almost silent act of expansion, a return to an idealized, unburdened length that the body hasn't known since it began to fight the pull of the ground in infancy. However, this temporary height gain is not without its cost, and it often arrives with an unwelcome companion, pain. The muscles in the back, long accustomed to their specific length and the constant work of maintaining posture against gravity, must suddenly adjust to this new, elongated state. Astronauts frequently experience discomfort, muscle spasms, or a deep, persistent ache during their first days and weeks in orbit. It is the body protesting the radical, almost instant change in its core structure. The slightly increased height also subtly alters how the astronaut moves within the confined quarters of the spacecraft, and how they fit into pressurized suits or narrow sleeping bags. Every subtle movement becomes a negotiation with a body that is no longer behaving as it once did. The consequences of weightlessness extend far beyond a momentary growth spurt. They touch the very strength and density of the skeletal structure. On Earth, our bones stay strong through a simple, constant demand. They must push back against gravity. This continuous low-level stress encourages the body to deposit minerals, primarily calcium, to keep the bones dense and load-bearing. In the suspended reality of microgravity, this essential physical demand disappears. The body, efficient and brutal in its adaptation, swiftly interprets this as a signal that high bone density is no longer necessary. The result is astonishingly rapid bone loss. Astronauts can lose nearly 1% of their bone mass every month they spend in orbit. This rate of degradation is alarmingly fast, far surpassing the most severe cases of osteoporosis experienced on Earth. Weight-bearing bones such as the femur, thigh bone, and the vertebrae in the spine weaken first, as they are the ones that have lost the most pressure. As the bone structure is slowly dismantled, the calcium that once fortified this tissue enters the bloodstream, eventually leaving the body through urine. This dramatic mineral shift is not harmless. It can place significant strain and risk upon the kidneys, which must process the excess calcium, introducing yet another health challenge in the zero-gravity environment. To counteract this silent internal erosion, astronauts adhere to an uncompromising daily routine of intense exercise. They spend hours every day strapped into specialized machines designed to simulate the resistance of Earth's gravity. These machines use elastic cords and pressurized systems to create an artificial pull, mimicking weightlifting and running motions. Yet even with this rigorous, non-negotiable exercise regimen, some degree of bone loss remains unavoidable. Recovery on return to Earth is a long, arduous process. As gravity reasserts its familiar presence, the spine gradually compresses back to its original shape, which can also be uncomfortable. Furthermore, it can take years for the lost bone mass to fully return, and tragically, not every astronaut recovers completely. Mission doctors and researchers study these changes with utmost focus, as they hold the key to the future of deep space travel. If humanity is ever to build cities on Mars, which has only a fraction of Earth's gravity, or to construct large rotating habitats in space, Understanding how the body adapts to and recovers from these different gravity levels will be absolutely essential for long-term health and the survival of our species far from home. The body's immediate surrender to microgravity is a quiet, profound lesson. Our existence is inextricably linked to the invisible force that shaped us. Our silent journey continues, moving beyond the physical sensations of the body to the sensory paradoxes of space itself. One of the most intriguing and subtle facts of orbital life is that the universe, often described as the perfect vacuum of absolute nothingness, is not entirely devoid of a sensory signature. While no human can actually breathe in space, astronauts returning from the focused isolation of a spacewalk frequently report a distinct aroma clinging to their suits, equipment, and tools once they re-enter the pressurized cabin and the airlock is opened. This invisible essence of the void leaves a profound, lingering trace. Astronauts struggle to define this cosmic scent with earthly vocabulary, but their descriptions are consistent and evocative. Some say it strikingly resembles the smell of hot metal, a sharp metallic tang. Others compare it to the brief, acrid smoke of burnt steak, or the harsh fumes produced by welding. This smoky, slightly burnt odor is not carried in from a distant nebula. It is created when high-energy particles, mainly solar wind and cosmic radiation traveling at incredible speeds, interact with the spacecraft's hull and the outer layers of the spacesuit. These high-speed interactions create highly reactive molecules that mix with the oxygen inside the cabin once the airlock is opened. These particles never reach the human nose directly in the vacuum, but they adhere chemically to the surfaces exposed to the void, leaving behind a profound and unforgettable trace. This sense of space, this metallic, high-energy aroma, is a silent, subtle sensory bridge between our protected environment and the incomprehensible depth of the cosmos. It serves as a quiet reminder that even in the profound silence and emptiness, the universe leaves its mark, a chemical signature imprinted on the metal and fabric that shields us. Researchers on Earth are deeply invested in studying these trace effects, using the astronaut reports as critical data points. Understanding the nature of these reactive molecules is essential for learning how to protect sensitive equipment and future deep space habitats from long-term, invisible exposure to the harsh elements of the void. The smell is a fascinating paradox. The universe is silent, yet it whispers its presence in the form of a faint, smoky memory. Moving from this invisible aroma to an overwhelming sight, we look toward the source of most of this energy, the sun, which looks completely and terrifyingly different when viewed outside the protective blanket of Earth's atmosphere. From our home planet, the sun appears as a soft, comforting yellow disk. This familiar appearance is an illusion, a magnificent trick played by the air above us, which scatters the most intense, high-energy light. In space, there is no air to filter its glare, no atmosphere to transform sunlight into the soft colors of dawn or dusk. The sun is revealed for what it truly is, a fierce, intense white sphere, blinding and razor-sharp, set against a perfect, absolute blackness. There is no blue sky to diffuse its brilliance, only the raw, powerful energy arriving without warning. Its heat is immediate and unfiltered, capable of burning through fabric, skin, or metal in mere moments if a spacecraft or astronaut moves out of shadow. The shadows in space are equally extreme, matching the blinding intensity of the light. They are pure darkness, absolute black, with no gentle fading at the edges. On Earth, our atmosphere scatters light into shadows, giving them a soft grey quality. In space, if an object blocks the sun, the resulting shadow is total, deep, and immediate. This dark contrast profoundly affects how astronauts perceive depth and distance during spacewalks, turning a simple motion into a complex visual calculation. It also dramatically changes how solar panels absorb energy and how cameras must record images. Every piece of equipment is designed around this intense, dualistic reality of total light and total dark. Every space mission must meticulously plan around this raw, unfettered light. The sun is the great paradox of space travel. It powers the spacecraft, feeding the solar panels with abundant energy, yet it simultaneously threatens every electronic system and creates a constant, unyielding hazard for unshielded humans. The intense white sun of the void is the constant, powerful reminder that Earth wraps us in a layer of atmosphere that performs an immense, invisible service. It is a filter, a gentle softening layer that stands between us and the full, unbridled violence of starlight. Without this subtle, protective presence, the most familiar object in our sky becomes an object of terrifying, silent power. As we settle further into the unique reality of orbital life, we turn our attention to the most basic, yet most transformed of human needs, the simple act of eating and drinking. In space, what nourishes the body must also adhere to the strict and unusual physics of microgravity. Food in space cannot crumble, it cannot leak, and it certainly cannot spoil, for a loose particle or an errant droplet poses a threat far greater than a simple mess. Consider the humble crumb. On Earth, a piece of bread that flakes away from the slice simply falls to the table or the floor. In space, a single crumb, dislodged from its source, instantly becomes a miniature, free-floating hazard, drifting aimlessly in the cabin air. If this tiny particle, lighter than dust, were to find its way into a ventilation fan, a sensitive sensor, or a critical control panel, it could potentially cause a system failure, jeopardizing the mission and the crew. Similarly, a drop of soup or coffee, if spilled from a container, would not fall. It would float away as a perfect, shimmering sphere of liquid, capable of silently drifting into delicate electronics, causing a short circuit or damaging a console. To avoid these persistent dangers, every single meal in orbit is a carefully calculated piece of engineering, designed to nourish without risk. The fundamental materials of food preparation must be rethought entirely. Bread, the common staple of Earth, is strictly forbidden because it sheds tiny, dangerous flakes. In its place, astronauts rely on tortillas, which are flexible, flat, and do not crumble. These can be used to wrap almost anything, serving as a versatile, low-risk edible wrapper. Drinks are a critical challenge. They cannot be served in open mugs or glasses. Instead, all beverages, from water to reconstituted fruit juice, are stored in sealed pouches and sipped through straws or specialized nozzles. This ensures that the surface tension of the liquid, which holds it together in a floating globe, is never broken in a way that allows it to escape into the cabin. Even spices, which are essential for flavor, must be managed with scientific precision. Salt and pepper, if sprinkled normally, would immediately fly away as a cloud of floating granules, contaminating the air and equipment. Therefore, they must be pre-dissolved in a small amount of water or oil and applied to food as a liquid suspension, allowing them to stick to the meal and be consumed safely. Fruits and vegetables that are brought up from Earth are often irradiated to kill any lingering bacteria, guaranteeing a shelf life and safety standard that removes all risk of spoilage in an environment where refrigeration is impractical or non-existent. Beyond the logistical challenges of containment, the act of eating is complicated by the body's own physical adaptation to the void. Without gravity to pull fluids down, they tend to collect in the upper body, giving astronauts a perpetual, mild sensation of being congested, a blocked nose or a heavy-headed feeling. This fluid shift, combined with the overall recalibration of the brain's senses, can significantly dull an astronaut's sense of smell and, consequently, their sense of taste. Food that would taste rich and savory on Earth can seem bland, muted, or faint in orbit. To combat this effect and maintain morale, spices are often much stronger than they would be in an Earth-based menu. Astronauts frequently crave bold flavors, intense sweetness, spicy sauces, and tanginess, finding classic comfort dishes too dull. Unexpected items such as shrimp cocktails served with extra horseradish or intensely flavored fruit drinks become highly requested favorites because they can cut through the dulling effect of the fluid shift. The process of preparing these meals is also far from traditional cooking. There are no ovens, no microwaves in the traditional sense, and no refrigerators for long-term storage, only specialized warmers that heat pre-packaged, vacuum-sealed trays. Cooking in orbit is less a culinary art and more a form of chemical engineering. Each dish is a miniature science experiment, designed not only to provide perfect nutrition but also to deliver flavor and consistency without taking any risks. The constant struggle to make food appealing in the face of biological and physical challenges underscores a crucial point. Long missions demand sustenance that nourishes both the body and the spirit, proving that in orbit, even a simple bite of food carries the science of human adaptation and survival. We now explore one of the most intimate and challenging acts of orbital existence, the quest for rest. On Earth, sleep is a submission to gravity, a process where we surrender our weight to a mattress held firmly against the surface by the familiar constant downward pull. In space, that pull is absent, and the entire ritual of slumber must be fundamentally relearned. There is no conventional bed in a spacecraft. If an astronaut were simply to close their eyes and relax without restraint, their body would begin to drift aimlessly. They would float through the cabin, bumping gently into sensitive equipment, walls, or even other sleeping crew members. The environment demands conscious, constant physical control, even in unconsciousness. To manage this, astronauts sleep inside padded, cocoon-like sleeping bags that are securely attached to the wall or ceiling of the spacecraft. These restraints are essential. They provide a vital sense of grounding, a simulated anchor in a world that offers none. Zipping into this sleeping bag, often located in a small closet-sized sleeping pod, is the final essential step in preparing for the night. The sensation of weightlessness during sleep is unlike anything experienced on Earth. While some astronauts describe the experience as profoundly peaceful, a gentle suspension that feels like eternal floating, others struggle deeply without the familiar pressure of lying down. The brain, confused by the lack of input from the inner ear's balance system, can produce strange and vivid dreams, illusions of falling or soaring, movements that the body is not physically making. Learning to reconcile the visual stability of the cabin with the internal sensation, seat. Continuous freefall is a skill that takes days, even weeks to master. The body must let go of its terrestrial expectations and embrace the quiet chaos of motion. But while the environment outside the hull is the epitome of silence, the interior of a spacecraft is never truly quiet. The silence of space itself is profound, but the necessary technology for human survival creates an endless, persistent soundscape. Life support systems are the crew's heartbeat, and they must run around the clock. Fans move air through filters to remove toxic carbon dioxide and control humidity. Pumps and valves click, whir, and hiss as they manage the closed-loop water and cooling systems. Computers hum steadily, marking the constant vigilance of the systems that keep everyone alive. Over time, this mechanical murmur becomes a background comfort, a steady white noise that signifies safety and continuity. The rhythm of these machines becomes the new measure of peace. However, this dependence also creates a heightened state of alarm if the familiar hum suddenly stops, or if an unexpected sound is heard, a new rattle, a strange groan, or an unusual tone. It can trigger instant, deep-seated concern. Silence inside a spacecraft is not peaceful. It is often terrifying, because it may signal that a critical life-saving system has stopped working. Furthermore, the structure of the spacecraft itself contributes to the nocturnal symphony. As the International Space Station orbits, it moves rapidly into and out of Earth's shadow, experiencing dramatic temperature swings. These quick transitions cause the metal hull to expand and contract, resulting in occasional soft pops, groans, and creaks that can be felt through the structure. Earplugs are often necessary for sleep, and some astronauts use personal white noise generators to soften the mechanical background. Despite these environmental conditions, a rigid sleep schedule must be maintained, often synchronized to Earth time, even though the spacecraft sees a sunrise every 90 minutes. This means the crew experiences 16 sunrises and 16 sunsets in a single Earth day. Learning to sleep in this continuously noisy, weightless, and time-shifted environment is a skill that demands tremendous mental adjustment and physical trust. Space travel demands restorative rest, but it offers none of the familiar comforts or natural quiet we take for granted on the ground, highlighting the unwavering reliance on technology for every single moment of life, even in the deepest moments of rest. Our attention now shifts to a profound truth of physics in microgravity, the simple behavior of water and other liquids, a behavior so fundamental on Earth, is utterly transformed in space. Without the gravitational pull to guide it, liquid ceases to flow downward. Instead, it is ruled by its own surface tension, turning the familiar into the strange. The most intimate and telling example of this transformation is the act of crying. Tears, which on Earth are pulled gently down the cheek by gravity, behave entirely differently in orbit. When an astronaut experiences a moment of emotion, or if an irritant triggers a natural flow of tears, the liquid does not fall, it clings. Tears form floating, shimmering blobs that adhere to the eye and the face, building up in a pool that grows, irritates, and blurs vision. They do not run away, they simply accumulate, often creating a painful, stinging sensation. Even the simple act of wiping tears away is difficult. A cloth, instead of absorbing and removing the moisture cleanly, may just spread the liquid into smaller spheres that continue to cling, or that drift away like tiny, wandering moons. These tear spheres can drift into the nose, or worse, get trapped beneath a contact lens, causing significant irritation and pain. The only way for an astronaut to clear this accumulated liquid is to blink repeatedly until the surface tension holding the tear globes breaks, allowing the moisture to float freely away, becoming a potential hazard in the cabin air. Emotional moments, allergies, or even stray dust from equipment can trigger this phenomenon. The strange, clumping behavior of tears is a quiet, powerful illustration of how far we are from home, a reminder that the human body evolved for gravity, and in space, even the simplest acts of human biology become exercises in physics. The transformation extends to all forms of water, shaping every aspect of life, from personal hygiene to essential consumption. Taking a shower, for instance, is impossible because water, released from a nozzle, would not fall in cleansing streams. It would form drifting, wobbling globes that float like tiny liquid planets throughout the room. Early mission tests with shower-style devices were quickly abandoned because the resulting droplets flew everywhere, potentially settling in wires and fans, creating immense technical risk. To stay clean, astronauts rely on carefully managed resources. They squeeze small amounts of water or rinseless soap onto their skin from sealed pouches and use gentle, absorbent towels to wipe their bodies. Even hair washing is a careful, choreographed routine. Water is massaged into the scalp, absorbed back into a cloth, or allowed to evaporate into the air filters for reclamation. Every drop is extremely valuable, too valuable to be wasted. The water within the closed-loop system is constantly recycled, purified from exhaled air, sweat, and even liquid waste. This makes water not just a necessity, but a carefully guarded resource, a molecule of survival that must be accounted for and reused endlessly. When water is poured or squeezed from a container, it forms perfect spheres, held together by the very surface tension that causes the tears to clump. A gentle touch can break one large sphere into several smaller globes, each one quivering and stretching like a bubble. Astronauts cannot drink from an open cup because the water would simply cling to the rim or form a mass that floats free. Instead, they sip from sealed pouches. This jelly-like behavior of water, almost seeming alive in its perfect, floating forms, is the dominant reality. Surface tension, a secondary force on Earth, becomes the primary sculptor of all liquid interactions, turning every drop into a soft, squishy shape that reminds the observer that even the most familiar substances behave like something entirely new the moment gravity lets go. Cleanliness, hydration, and even emotional expression in space become profound, careful practices of adaptation to a world where physics has been dramatically redefined. Having explored the internal, contained world of the spacecraft, we now turn to the ultimate act of commitment and isolation in space travel, the spacewalk, or extravehicular activity, EVA. When an astronaut leaves the safety of the airlock, stepping out into the open void, they cross a profound threshold. Every danger previously managed by the layers of the ship becomes immediate, real, and personal, transforming a task into one of the most dangerous things any human being can attempt. The astronaut is encased only in the spacesuit, the tiny, pressurized bubble we discussed earlier. The stakes are absolute. One tiny, unseen tear in the material, one catastrophic malfunction in the life support system could mean death in a matter of seconds. Out in the full, unshielded exposure of orbit, the environment is relentlessly violent. Temperatures can swing from the blistering heat of direct sunlight, hot enough to instantly scald, to the freezing cold of absolute shadow, frigid enough to turn fluid solid, all in the time it takes to move an arm. The body must constantly pass through this transition, and the suit's thermal systems must manage this extreme, instantaneous conflict. Movement itself is fraught with peril. In the total absence of friction, the slightest uncorrected force, a tiny bump or an accidental push, can send a person drifting gently away from the secure tethering of the spacecraft. Once free, they are on a path to nowhere, a helpless satellite of their own until and if they can be recovered. To prevent this, every motion is anchored. Astronauts are constantly secured by heavy, specialized tethers, lifelines that are clipped, checked, and managed at all times to maintain a physical connection to the ship. Even the simple automatic act of breathing is a managed risk. The suit's internal atmosphere must be perfectly balanced and controlled to avoid twin dangers: oxygen toxicity, where too high a concentration of pure oxygen can become harmful, or carbon dioxide buildup, where exhaled gas is not scrubbed efficiently enough, leading to rapid contamination. The astronaut must spend hours preparing in a low-pressure environment before the spacewalk begins, a process known as pre-breathing, to purge nitrogen from their body and prevent the painful, crippling condition known as the bends. The environment outside demands precision that borders on the unnatural. Tools must be carefully secured, often to the suit or the workstation, each one tethered to prevent it from floating away and becoming a piece of dangerous space debris. Every motion of the task, from turning a bolt to replacing a battery, is rehearsed again and again thousands of times. In the deep silence of massive underwater training tanks on Earth, these neutral buoyancy laboratories simulate the exact sensation of weightlessness and resistance, ensuring that when the astronaut is performing a task with potentially fatal consequences, the muscle memory is flawless. Despite all this preparation, every spacewalk inherently carries the terror of the unknown. The silence surrounding the astronaut is not the peaceful quiet of a natural landscape. It is the deep, profound silence of a place where life does not belong, where the environment is actively and instantly hostile. The only sound the astronaut hears is the whirring of their own suit's fans, the gentle sound of their own breathing, and the voice of mission control in their helmet, a constant vital link to the safety they left behind. The human body, enclosed in this technological shell, becomes a point of deep vulnerability, surrounded by absolute vacuum and high-energy particles. The entire experience of a spacewalk is a testament to technological prowess and human courage, but it is also a quiet, constant reminder that we are intruders here. Each movement is slow, deliberate, and expensive, a negotiation with physics itself. Out on the exposed surface of the spacecraft, gazing at the perfect blackness of space and the incredible curving blue of Earth far below, the astronaut is utterly alone, separated from safety by mere millimeters of engineered material, relying entirely on the perfect function of their own personal bubble at the very edge of human experience. As we move away from the physical dangers of vacuum and extreme temperature, we encounter a threat that is silent, invisible, and persistent: space radiation. This is a constant, high-energy bombardment that penetrates materials and bodies, posing one of the greatest long-term challenges to human health and deep space exploration. Outside the protective, comforting blanket of Earth's magnetic field and dense atmosphere, the human body is relentlessly exposed to an invisible storm of cosmic ray, YS, and solar particles. These particles are not gentle waves of light. They are high-energy atoms and fragments of distant stars, supernovae, and black holes, traveling across the universe at incredible near-light speeds. When these particles strike a spacecraft or an astronaut, they pass through metal, tissue, and even skin, slicing through the most fundamental blueprint of life, the DNA inside cells. The result is broken strands or unwanted mutations, a silent molecular damage that accrues day after day. On Earth, we are largely unaware of this danger because our planet provides a magnificent natural defense system. The Earth's magnetic field acts like a gigantic, invisible shield, diverting the majority of charged particles away from the surface. Our thick atmosphere then absorbs and scatters much of what remains. But in the unprotected expanse of space, astronauts receive radiation doses far above the levels that are considered safe for long-term human health. This continuous exposure can lead to severe and cumulative health risks, including a significantly increased lifetime cancer risk, a noticeable weakening of the immune system's ability to fight infection, and even the clouding of the eyes. The body, constantly fighting this unseen energy, is under perpetual stress. Engineers are in a constant battle against this invisible force, developing advanced shielding for future spacecraft and deep space habitats. Protecting the human body from particles that arrive from every direction is a profoundly complex challenge. Current spacecraft use thick layers of material, sometimes even surrounding the crew's sleeping quarters with water tanks or food supplies, which offer a dense temporary form of shielding. However, every layer of protection adds weight, and weight is the enemy of efficient space travel. Balancing the necessity of safety with the limits of propulsion and cost is a difficult, ongoing negotiation. The invisible storm of radiation is dramatically punctuated by unpredictable solar flares and massive bursts of energetic particles called solar storms. The sun, a source of life and warmth, can erupt violently, blasting these dangerous particles across the solar system at tremendous speeds. During a strong solar storm, radiation levels inside a spacecraft could exceed safe limits within hours. When this threat is detected, crews must quickly retreat into specialized, heavily shielded storm shelters. These shelters are designed to provide maximum protection in a minimum of space, often built into the ship's core. Plans for long-duration missions to Mars must include these emergency shelters and reliable, fast-acting warning systems to predict the arrival of a solar event. This constant, invisible hazard is one of the biggest barriers to humanity's dream of deep space missions, especially the multi-year journey to Mars. Every day spent in orbit or traveling farther from Earth reveals more about this danger that follows astronauts wherever they go. The knowledge we gain from studying its effects is critical, reminding us that the universe is not an empty, benign place, but a chemically and energetically active environment. The human body is a marvelous machine, but outside the cradle of our planet, it requires a continuous, engineered defense against the constant, quiet threat of the cosmos. Space radiation is the silent killer, and managing it is the ultimate test of human engineering in the face of natural law. Having discussed the predictable threats of vacuum and radiation, we now confront a danger that is startling in its familiarity, yet profoundly strange in its behavior: fire. On Earth, we understand fire implicitly. It is a fierce, upward-reaching element, its flame shaped by the buoyancy of hot air. In space, Re sheds its earthly instincts, transforming into a slow, ghostly enemy defined by the absence of gravity. A flame on Earth flickers and climbs upward, sustained by the constant process of convection. Hot, less dense air rises, pulling cooler, denser air filled with fresh oxygen down to feed the base of the fire. In the microgravity of a spacecraft, there is no upward or downward motion because there is no gravity to create density differences. This simple absence of buoyancy completely changes the chemical and physical dynamics of combustion. Without the pull of gravity to draw in fresh oxygen, flames cannot flicker or grow tall. Instead, they burn as perfect, delicate blue spheres, floating eerily in place. These ghostly orbs consume oxygen slowly and evenly from all directions, creating a beautiful, yet terrifying, form of combustion. The lower intensity of the burn might seem like a benefit, but it introduces far greater problems. The primary issue is the movement of smoke and toxic gases. On Earth, smoke rises swiftly, triggering alarms and allowing the source of the fire to be quickly located and ventilated. In space, smoke does not rise. it simply accumulates in confused, toxic clouds hovering silently around the source of the burn. A small electrical flame in a corner of a spacecraft, burning slowly as a pale blue sphere, can silently fill the room with toxic gases, carbon monoxide and other lethal byproducts, before fire alarms, which often rely on significant temperature changes, can even register the danger. The fire is harder to detect and harder to track because it is trapped by its own byproducts. For this critical reason, every single material brought aboard a spacecraft, from insulation and plastic coverings to electronic wires and even personal items, must be rigorously tested for its reaction to fire in a zero-gravity environment. Engineers focus obsessively on flammability, choosing materials that either self-extinguish quickly or produce minimal, less toxic smoke when burned in a low-convection setting. The materials science of space safety is a constant, precise, and necessary effort to preemptively neutralize this unpredictable element. Fire drills for astronauts are therefore drastically different from any practiced on Earth. They are not about swiftly fleeing a rising inferno. They are designed to teach crew members how to manage systems in darkness and confusion, how to seal hatches to contain the spread of toxic air, how to shut off ventilation systems that could spread the contaminated atmosphere throughout the ship, and, most crucially, how to locate and use extinguishers against a flame that does not behave as expected. The crew must learn to fight an enemy that moves in all directions at once, a quiet, accumulating menace. The fire threat highlights the fundamental difference between living in a natural and an artificial environment. Fire on Earth is dangerous and dramatic, a powerful force of nature. But fire in space, domesticated by physics into a slow, perfect spherical burn, becomes a quiet, insidious enemy. It is a constant, subtle reminder that the life support systems, the ventilation, and the air itself are not gifts, but meticulously managed resources. The air that gives life can quickly turn toxic, and a small spark, instead of flaring dramatically, can become a silent, pervasive disaster, testing the very limits of human engineering and quick thinking far from any possibility of outside help. We return now to the outer edge of the spacecraft, to the environment of the spacewalk, and focus on the necessity of control in a world that offers none, in the meticulous ballet of an extravehicular activity where every item must be handled with utmost precision, the loss of even the smallest object carries implications that extend far beyond a simple inconvenience. A lost tool can become a permanent high-velocity threat. This reality gives rise to the principle of tethered existence. An astronaut working outside the ship handles hundreds of items, wrenches, cameras, clamps, specialized tethers, and complex instruments. In a world without gravity or friction, the moment an object leaves a hand, it does not fall, it simply begins to drift, following the last momentum it received. Despite the careful, rigorous training, a few tools inevitably slip away. Once free, these objects do not stop. They escape the immediate workspace and settle into the orbit of the spacecraft, instantly transforming into tiny human-made satellites circling the Earth. One of the most famous examples of this orbital detritus was the loss of a full tool bag by an astronaut during a spacewalk. This bag, containing essential instruments, floated away, eventually becoming a detectable object that could be tracked from Earth with binoculars, a fast-moving, accidental relic of human activity. These lost items are harmless on their own, but they contribute to a far more profound and escalating danger, the growing cloud of space debris. Earth's orbit is a crowded, vast, yet increasingly contaminated highway. It is filled with the unintentional leaves of 60 years of space exploration, decommissioned satellites, fragments from old rocket stages, microscopic paint chips knocked loose during collisions, and yes, lost tools. Every single piece of this junk is traveling at tremendous orbital velocities, tens of thousands of kilometers per hour, far faster than any rifle bullet. At these speeds, even a minuscule fragment, the size of a grain of sand or a tiny shard of metal, carries enough kinetic energy to be a catastrophic threat. Such an impact could puncture a spacesuit, shatter a spacecraft wing, dow or disable critical electronics, Larger fist-sized chunks could destroy an entire satellite or even compromise the International Space Station itself. The danger of this debris is that it fuels a cascading, self-perpetuating problem. The more objects that are in orbit, the higher the probability that two of them will collide. When a crash occurs, it does not simply eliminate two pieces of junk, it creates a massive cloud of thousands of new fragments, each of which is then capable of causing another collision. Scientists fear this escalating chain reaction, known as the Kessler effect, which could someday turn certain low Earth orbits into deadly, unusable fields of shrapnel. This nightmare scenario threatens to trap us on Earth, making safe egress from the atmosphere nearly impossible for decades. Therefore, for the astronaut during a spacewalk, the requirement for tethering is not just about efficiency, it is about planetary safety and the future of exploration. To prevent chaos, every wrench, every pen, every piece of equipment is labeled, tracked, docked, and most importantly, clipped to a suit, a wall, or a looped cable. There is no concept of casually setting something down. The entire world must be tied down one item at a time. Living in microgravity means relearning how to interact with every object, treating it not as a simple tool, but as a potential missile. Mission Control tracks thousands of larger pieces of debris in real time, often having to adjust the International Space Station's orbit to dodge incoming fragments. But the micrometeorites and the tiny undetectable shards remain an omnipresent risk. Space is vast beyond comprehension, but orbits are narrow and becoming tragically crowded. Every single launch, every accidental loss of a screwdriver, every tiny fleck of paint adds to a risk that the next generation of space travelers will have to manage. Tethered existence is a profound reminder that human habits, built for a world of falling objects and friction, must be replaced by a careful, almost religious devotion to containment in the zero-sum reality of space. Our journey now takes us to the deepest frontier of space adaptation, the human mind and its sensory perception. The moment gravity is removed, the brain must confront a world that completely defies its earthly programming, leading to profound and often uncomfortable shifts in how we taste, move, and understand our own orientation. We first revisit the strange world of taste, which is drastically altered in the floating environment. Food that might be rich and savory on the ground often seems dull, faint, or muted in orbit. This shift is not merely psychological, it has a direct physical cause. Without gravity pulling fluids into the lower body, blood and other fluids accumulate in the chest and head. This fluid shift creates a constant sensation akin to having a head cold or mild congestion, which significantly reduces an astronaut's sense of smell. Since the majority of what we perceive as taste is actually derived from scent, the ability to fully enjoy flavor is drastically diminished. Simultaneously, the brain is actively recalibrating, attempting to make sense of a body that feels perpetually suspended. To cope with this sensory dulling, astronauts develop intense cravings for bold, sharp, and highly aromatic flavors. They seek spicy sauces, tangy fruit drinks, and foods with extra heat, finding that only these intense stimuli can cut through the constant mild congestion. Classic comfort foods often fall flat, while unexpected dishes, like shrimp cocktail with an extra dose of horseradish, become sought-after favorites. This alteration in taste is more than a culinary curiosity. It is deeply connected to appetite, nutrition, and morale. Long-duration missions require food that can satisfy these altered senses to ensure that the crew maintains a healthy diet and a positive mental state. In orbit, every meal becomes a carefully tested scientific component, ensuring the nourishment of both body and spirit in a world where familiar flavors have vanished. The shift in taste is closely tied to a more profound challenge: space sickness, which can be likened to seasickness, only far worse and more disorienting. The human balance system is a complex architecture of the inner ear, eyes, and proprioceptors, sensors in the muscles, that constantly interprets gravity, motion, and body position. When gravity is suddenly removed, the inner ear, designed to sense up and down, stops providing a steady flow of directional information. The brain receives strange and conflicting signals. The eyes see a stable, fixed environment inside the cabin, but the inner ear reports a continuous state of free fall. This sensory mismatch causes acute space adaptation syndrome, which strikes many astronauts during their initial days in orbit. Symptoms include severe nausea, vomiting, dizziness, and intense disorientation, often making it difficult to work, eat, or even sit comfortably. Medical teams prepare for this with carefully administered medication and a slow introduction to physical tasks. While the symptoms are profoundly unpleasant and can temporarily ground mission tasks, the brain eventually adapts. This process, however, can take days, sometimes weeks, as the mind learns to prioritize visual cues over the missing gravitational data. The inner ear is, in effect, ignored until the brain constructs a new internal map of its surroundings. The disorientation of microgravity also extends to orientation. In space, there is truly no up or down. Walls, floors, and ceilings have no intrinsic meaning. Astronauts often feel fundamentally confused, or even upside down, even when floating upright. Simple tasks like reaching for a toolbox or turning a corner inside the spacecraft become mental puzzles until the mind reorganizes itself. Objects no longer fall when dropped, and muscles no longer stabilize the body automatically. Every movement must be consciously relearned with care and precision. This radical shifting of reality is one of the most profound psychological and physical challenges of life in orbit. The necessity of relearning movement and recalibrating the senses is a quiet reminder that the body we carry, the instincts we trust, and the flavors we love are all deeply, intricately built for Earth's familiar gravitational pull. Learning to let go of gravity does not just change how the body moves, it fundamentally changes how the mind feels at home in the universe. We now arrive at a profound truth of sustained life beyond Earth. The spacecraft, or habitat, is not just a shield against the void, it is a meticulously engineered, self-contained planet. Unlike Earth, where air, water, and food surround us effortlessly, a spaceship must bring, manufacture, filter, and recycle every single molecule necessary for human life. This is the closed ecosystem challenge. The most vital component of this artificial world is the atmosphere itself. Inside the spacecraft, breathing is not a reflex, it is a technology problem. The air must be precisely controlled, a balanced artificial mix of nitrogen and oxygen that mimics Earth's breathable air. The oxygen supply must be constantly replenished, either drawn from high-pressure tanks or generated through a complex process called electrolysis, which splits water molecules into hydrogen and life-giving oxygen. But providing oxygen is only half the battle. As the crew breathes, they exhale carbon dioxide, which is toxic at elevated levels. This harmful GA must be constantly removed from the air using chemical filters known as carbon dioxide scrubbers. These systems use specialized materials to trap the gas molecules before they can build up, ensuring the air remains fresh and safe. At the same time, humidity must be precisely managed. Too much moisture in the recycled air can lead to condensation, which could settle on surfaces, short-circuiting electronics or encouraging mold and mildew. Too little, and the air becomes dry and uncomfortable. Every single parameter, pressure, temperature, oxygen level, carbon dioxide level, and humidity, is tracked with relentless vigilance. Every system that supports this artificial atmosphere has multiple layers of redundancy. There are backups for the fans, spare filters for the scrubbers, and emergency oxygen masks and pressure suits in case of a sudden depressurization event, a rupture in the hull that would allow the precious air to escape into the vacuum. The air within the spacecraft is a fragile, life-giving gift that must be built, protected, and renewed every single moment the crew is far from home. This concept of self-sufficiency extends beyond air to encompass the entire resource chain, especially for long-duration missions like those planned for Mars. A successful human settlement cannot rely on constant resupply from Earth. The distance is too great and the cost too prohibitive. Instead, a Mars colony or a deep space habitat must function as a true sealed ecological system, a small planet within walls where everything is recycled, Water, the ultimate resource, must be recycled endlessly. Every drop, purified from humidity, recovered from sweat, and processed from even liquid waste, is reclaimed and reused through complex filtration systems. Waste matter is not discarded. Solid waste is compressed, stored, or sometimes even broken down by engineered bacteria and utilized to grow new crops. Plants, grown in pressurized greenhouses under artificial light, become essential partners in this closed loop, converting carbon dioxide back into oxygen while simultaneously providing fresh food. This closed ecosystem principle dictates the entire design of the habitat. Airlocks are the critical gateways separating the living world from the alien landscape outside. Energy must come from solar farms or potentially small reactors. Even clothing, tools, and spare parts must be repaired, recycled, or 3D printed on site using local materials. On Mars, where breathing will require the constant mechanical splitting of carbon dioxide or the extraction of water ice, breathing becomes an active technological process, not a birthright. The habitat must act like a living organism, balancing every resource with precision. The construction of these self-sustaining worlds, whether the International Space Station or a future Martian dome, is the quiet, persistent triumph of science over nature, demonstrating that humanity can in fact build its own small piece of Earth to carry with it into the vastness of the cosmos. Our quiet voyage now takes us closer to home, to the silent, airless surface of the Moon, a world where the very ground beneath our feet holds a dual nature, a timeless museum of human effort and a subtle, persistent threat to human life. This is the reality of the lunar legacy, forever marked by dust and silent boot prints. When the Apollo astronauts stepped onto the Moon, they left behind indelible traces of their visit, boot prints, the tracks of the lunar rover, and marks from their tools. Because the Moon has no atmosphere, no wind, no rain, and almost no geological activity to disturb its surface, these impressions are frozen in time. Without the forces of erosion that constantly reshape Earth, those footprints may last for millions of years, remaining as fresh and distinct as the moment they were made. They are like scattered fossils of human exploration, quiet trails across the dust, telling the story of the few brief days when humanity first visited another world. This scene is both beautiful and haunting, a permanent record that, once we touch a world without weather, we leave a mark that time forgets to erase. Yet, the ground that records this history also presents one of the most unexpected and pervasive hazards: lunar dust. This dust is not like the soft, smooth, rounded grains of beach sand we know on Earth. It is utterly alien, sharp, jagged, and abrasive, formed by billions of years of high-speed meteoroid impacts that shattered rock in the absence of wind and water. These forces have created particles with razor-sharp edges that adhere magnetically and statically to everything they touch. During the Apollo missions, astronauts returned to their lander covered in this fine grey powder. The dust was so pervasive that it smelled distinctively like burnt gunpowder, a scent that only became noticeable once the dust met the oxygen inside the cabin. Once inside, this abrasive powder clung to every surface, worked its way into the fabric and seals of the spacesuits, and scratched the helmet visors, gradually degrading these vital layers of protection. More dangerously, the fine particles irritated the astronauts' lungs and eyes, posing a long-term respiratory risk if not managed. Future moon missions will involve extended stays, lasting far longer than the few days of the Apollo era, which means this dust must be managed with absolute diligence. It is a silent, ever-present threat ready to tear through the fragile technology that protects human life. Engineers are currently designing new strategies to fight this menace, including special electrostatic systems that might repel the dust or physically shake it loose before astronauts enter the airlock, and materials coated with special non-stick compounds. The challenge is immense, as the dust's sharp nature and adhesive properties make it difficult to contain. The lunar dust is a quiet warning. Even the ground beneath our boots on another world is hostile and alien, designed to wear down technology and challenge human biology. The legacy we left behind, those first perfect footprints, symbolizes both our capability to reach the stars and the immense difficulty of staying there. We walk across a geological time capsule, but we do so knowing that the very substance preserving those marks is actively trying to infiltrate and destroy the environment we have built to survive. The moon is a world of silent, deep time, a place where the smallest particle of dust holds the power to become a deadly contaminant, demanding respect and unrelenting caution from all who dare to visit. While focus shifts now from the quiet proximity of the moon to the alluring distant horizon of Mars, the red planet, this world holds a rhythm all its own, a slower, stretched-out tempo that future human settlers will have to adopt entirely, abandoning the familiar cycles of Earth time. Mars is a world of magnificent extremes, defined by its thin air, long years, and astonishing visual paradoxes. A day on Mars, known as a sol, is remarkably close to our own, but just slightly longer. It lasts 24 hours and about 40 minutes. This small difference, an extra 2/3 of an hour, means that over the course of a long mission, the Martian day constantly slips out of sync with an Earth-based clock. Future settlers will need new clocks and calendars entirely, tuned to the Martian soil. Work shifts, sleep cycles, and planting schedules will all follow the local Martian sunrise and sunset, not the rhythms of a distant homeworld. This transition marks a profound psychological separation. Time itself will no longer be something shared, but a unique part of their Martian identity. More dramatically, Mars orbits the Sun more slowly than Earth, meaning a Martian year is almost twice as long as ours, taking nearly 687 Earth days to complete one circuit. As a result, Mars experiences seasons, but they are stretched and extended. Winters are long and frigid, reaching temperatures far below any found on Earth. Summers are milder, but are often accompanied by massive, planet-engulfing dust storms. These dust storms are a defining feature of the Martian environment. They can start in a single region and slowly spread until they cover the entire planet, sometimes lasting for months. During these global events, Mars becomes a hazy, muted sphere. Sunlight is reduced to a faint orange glow even at midday, plunging the surface into perpetual twilight. The dust, composed of sharp, iron-rich minerals, lingers in the thin air, clogging filters, blocking solar power, and coating every exposed surface. Living on Mars will require shelters strong enough to withstand these storms and energy systems, such as nuclear power banks, that can function without sunlight for long periods. On this planet of red dust, the weather becomes a tremendous long-term force that demands respect and constant adaptation. Amidst these extremes, Mars holds a surprising, ethereal beauty that defies our expectations. One of the most stunning paradoxes is the Martian sunset, which is not red or orange like Earth's, but a soft, deep blue. On Earth, our dense atmosphere scatters the blue wavelengths of sunlight across the sky, leaving the red and orange light to color the horizon at dusk. On Mars, the opposite occurs. The thin Martian air is filled with fine iron oxide dust particles. These particles scatter the red light away, allowing the blue wavelengths to slip through or directly. As the sun dips toward the horizon, the sky immediately surrounding it fades into a subtle, almost dreamlike blue halo. The rest of the sky stretches into warm butterscotch and rose tones. Because the atmosphere is so thin, the colors are delicate, like a watercolor painted by a quiet universe. Future astronauts will one day stand on Martian soil and witness these gentle blue sunsets, seeing a sky no human eyes ever witnessed before the space age. This vision reminds us how dramatically different worlds can be, yet how every corner of the cosmos holds its own unique and silent beauty. Adapting to the red planet's rhythm means embracing a world where time, weather, and light are all fundamentally and gorgeously alien. We now trace the final difficult leg of the journey, the quiet, profound challenge of returning to the world that shaped us. After months spent in the gentle suspension of microgravity, where movement was effortless and weight non-existent, the human body has to confront the relentless, familiar force of Earth's gravity all over again. The process of readaptation is not an instant relief, but a physical and neurological ordeal. The moment the returning spacecraft lands and the astronaut stands up, the effects of long-duration spaceflight become agonizingly clear. After the body has forgotten how to carry weight, the legs feel impossibly heavy, as if anchored by lead. Muscles have shrunk, bones have lost density, and the nerves that coordinate balance and simple movement are out of practice. The entire body frame, which was built for gravity, struggles to remember its original programming. One of the most immediate and startling effects is on the cardiovascular system. In space, blood floats evenly through veins and arteries, accumulating in the chest and head. The heart does not need to work as hard, and over time it can begin to shrink, losing the muscle mass required to fight Earth's gravitational pull. The moment the astronaut is back on the ground, gravity instantly pulls the blood downwards, a process called fluid shift. The returning astronaut becomes instantly lightheaded and dizzy, often struggling just to stand upright without fainting, as the heart struggles to pump blood back up to the brain against the weight it hasn't felt for months. Doctors must monitor circulation constantly, ensuring the body does not suffer dangerous clotting or low-pressure fainting episodes. Simultaneously, the skeletal system faces a painful reversal. The spine, which had stretched by several centimeters in orbit, gradually compresses back to its original length, a change that can cause deep discomfort and pain in the back muscles. The bones, having lost up to 1% of their mass per month, are weaker, lighter, and more fragile. The body must begin the slow, arduous process of rebuilding density, a process that can take years, and one that is never fully guaranteed for every astronaut. The brain, too, must entirely relearn how to balance. The inner ear's vestibular system, which spent months trying to reconcile the sensation of free fall with a stable environment, is now flooded with the sudden, powerful signals of gravity. This sensory confusion can cause persistent dizziness, disorientation, and unsteadiness. Simple tasks like walking in a straight line, judging distance, or even coordinating hand and eye movements become mental puzzles. Doctors, physiotherapists, and trainers work hard with each astronaut. They begin with short, carefully monitored sessions, sometimes requiring the astronaut to wear harnesses to practice walking safely on a treadmill, preventing sudden falls. They focus on rebuilding the specific strength in the legs and core, coordination and confidence, pushing the body to accept the familiar weight of home. This process can take weeks or months before the astronaut returns to normal, confident motion. This physical ordeal upon return is not just a medical challenge, it is a profound emotional one. It is a quiet, powerful reminder that our existence is fundamentally defined by the worlds we inhabit. The struggle to simply walk, to stand, and to breathe comfortably under the steady pull of gravity offers a preview of what humans might face on Mars or other worlds where gravity is different. Relearning to walk is the final, essential chapter of the space mission, a humbling affirmation that our bodies are shaped and continually reshaped by the silent, powerful force of the Earth we briefly left behind. We now leave the immediate confines of our solar system and look toward the concept of deep space, where the very nature of time itself begins to warp and shift. This is the domain of time dilation, a phenomenon predicted by Albert Einstein, which reminds us that the universe is not a single ticking clock, but a collection of rhythms shaped by motion and gravity. Astronauts aboard the International Space Station, orbiting the Earth at incredible speeds, are already proving this theory right, because they are moving so fast and are situated slightly farther away from Earth's center of mass, experiencing slightly less gravity. Time for them moves just the tiniest bit slower relative to people on the ground. The effect is minuscule, a fraction of a second over the course of an entire mission, nearly impossible to notice in a human lifetime. But it is real and measurable with the most precise atomic clocks. They age a fraction of a second less than those who remain on Earth. This subtle difference is a profound confirmation. Time is a flexible thread, stretching and contracting depending on the journey. If we ever send humans to the far reaches of the solar system, or, more dramatically, to other stars, this effect will grow stronger. A traveler journeying for decades at speeds approaching that of light would return to find that far more time had elapsed on Earth. They could arrive home younger than their siblings, finding entire generations gone. The universe keeps time as a dynamic landscape that humans must learn to navigate, where a rapid journey means a slower passage of moments for the traveler. This bending of time is a central factor in imagining the most ambitious form of human endeavor, the generation ship. The closest star beyond our sun is over 20 trillion miles away. Even with the fastest theoretical propulsion we can conceive, a ship traveling to a distant star system could take decades, centuries, or even millennia to arrive. No single crew could live long enough to complete such a trip. The only solution is to build a world that travels. A generation ship is a massive vessel designed to carry entire communities. Within its hull, a self-contained closed ecosystem, a small artificial planet, would sustain a population for the duration of the voyage. Children would be born, live and die without ever seeing Earth or the destination. Every necessity of civilization would exist inside the spacecraft: schools, food systems, medical bays, repair shops, and social structures. The mission would span generations, spanning dozens of human lifetimes. The challenge is as psychological and sociological as it is technological. The crew of the 10th generation, far removed from the original mission objectives and the memory of Earth, would need a strong, stable culture to maintain the ship and its purpose. The hull itself would become their only world, drifting between the stars, a home where the stars outside are fixed and unmoving, and the concept of a natural sunrise is unknown. The people inside might develop their own unique culture, laws and beliefs, entirely distinct from the terrestrial civilizations they left behind. If they succeed, the descendants of the original crew will one day step out onto a new world, orbiting a new star, carrying with them only the faint inherited memory of a planet they never knew. The journey is not merely a transit across space, it is a profound passage across time, a living history carried forward by lives yet to be imagined. Time dilation suggests that, while the journey may take centuries from Earth's perspective, for the travelers, time will be their most precious, flexible, and essential commodity, stretching and contracting as their vessel hurtles through the cosmos toward a future star. Our quiet observation now turns outward to the stunning, active visual phenomena that define the outer edge of our planet's protection, the silent fireworks and the living halos of light, visible only to those in orbit. Here, the astronaut is an eyewitness to the profound, continuous interaction between the Earth, the Sun, and the distant cosmos. One of the most surprising phenomena reported by astronauts is the sight of shooting stars or meteors visible inside the spacecraft. While resting in darkened cabins or looking through the dim corners of the station, some astronauts report seeing sudden, quick streaks or flashes of light. These phantom sparks are not necessarily seen outside in the void. They are often caused by cosmic rays, high-energy particles from distant stars and black holes, traveling at speeds approaching light. When these powerful particles pass through the spacecraft's hull and the astronaut's body, they sometimes strike the sensitive retina or the optical nerves. This impact triggers a flash or streak of brightness, a brief, luminous sensation that appears out of nowhere, even when the eyes are closed. This effect is a constant, subtle reminder that the universe is actively bombarding everything, everywhere. These cosmic rays are a major component of the invisible storm we discussed earlier, and their ability to trigger light flashes in the eye is a direct illustration of how radiation affects the human body and brain. For future explorers venturing into deep space, where radiation exposure is even higher, these brief, unexplained sparks may become constant low-level companions, the universe sending constant, silent reminders of its hidden violent forces. Alongside these internal flashes, the astronauts also witness the more familiar, yet infinitely more magnificent, spectacle of micrometeorites striking the exterior of the spacecraft. When tiny dust particles or micrometeorites collide with the hull at terrifying speeds, they release a burst of energy, creating glowing streaks of light visible through the windows. Each one of these visible flashes is not a harmless twinkle. It is a collision happening faster than any bullet, slowly carving microscopic craters into the glass and aluminum of the spacecraft's shell. While humbling and beautiful, these impacts are tracked and accounted for, a measure of the constant, gentle wearing down of the fragile metal shelter that keeps the crew alive. Even more breathtaking is the silent, ethereal dance of the aurora, the northern and southern lights. On Earth, we see the aurora as curtains of shimmering green and red light on the horizon. From orbit, the view is transformed. Astronauts look down and see the aurora from above, appearing as immense, glowing rings of light that circle the magnetic poles. These waves of color dance across the thin edge of the atmosphere, like ripples in a pond of cosmic energy. The light itself is generated by charged particles from the sun, the solar wind, colliding with gases in Earth's atmosphere which are funneled by our planet's magnetic shield. Seen from orbit, the aurora looks like a living halo around the planet, shifting, pulsing, and expanding with the intensity of solar storms. Sometimes the glow is so bright that it illuminates the snow on the surface far below. Astronauts often pause their work to watch the colors move silently beneath them, a majestic and constant performance that speaks to the power of our planet's protective field. Seeing the aurora from above reminds the observer that Earth is not merely a planet of rock and water, it is an island of energy and life, wrapped in an active, powerful magnetic cocoa. These celestial sparks, whether the invisible flashes in the eye or the colossal, dancing rings around the poles, reinforce the profound connection between the micro-world of human biology and the colossal forces of the cosmos, a silent testament to the drama occurring constantly at the boundary of life and the void. We approach the conclusion of our journey by considering the deep future of humanity in space, a future defined by robotic pioneers, the possibility of irreversible journeys, and the eventual quiet evolution of the human form itself. This is the story of humanity becoming a multi-planet species. The first homes built on Mars may not be constructed by human hands. Before humans ever step onto Martian soil to stay, robots may arrive years ahead of them to act as the true first builders. These autonomous robotic pioneers could use the planet's own dusty, iron-rich soil, called regolith, mixed with special binders, to 3D print the first protective walls and habitats. This approach is dictated by simple economics and physics. Transporting millions of kilograms of building materials from Earth is costly and impractical. By utilizing the local resources, the robots turn the lonely planet into a quiet, preparatory work site, digging trenches for wiring, assembling solar arrays, and setting up the initial life support systems for incoming crews. This strategy means astronauts could land with pre-made, pressurized homes, power, and air systems instead of scrambling to build everything upon arrival. The first safe foothold on another world will likely be a triumph of machine intelligence, making life possible where no life yet exists. This preparation is crucial, for the human journey to Mars carries a stark and profound implication. The first humans to set foot on the red planet may never return to Earth. A one-way choice is a possibility rooted in logistics ND biology, not a lack of desire. The journey itself takes many months, and once there, the sheer amount of rocket fuel needed to launch from the Martian surface must either be brought from Earth, an immense logistical impossibility, or manufactured on the planet using local resources. Even if the fuel is produced, the journey home would take just as long, subjecting the travelers to years of low gravity and radiation exposure. Some mission plans quietly suggest that the first explorers may remain permanently, transitioning from visitors to the first settlers, dedicating their lives to building the foundation of a new civilization. Returning home after years away would be physically devastating. Bones, muscles, and organs would struggle to readapt to Earth's full gravity. The decision to go to Mars may become a one-way commitment, not necessarily because the technology to bring someone back won't exist, but because their body might not survive the process of readaptation. Mars may someday become a new cradle of humanity, but it may require pioneers willing to stay forever. Finally, we contemplate the farthest reach of this isolation, human evolution on other worlds. If humans successfully build colonies on Mars, the Moon, or in large space habitats, and begin raising children there, natural evolution may start working along completely new paths. The lower gravity of Mars could change height, posture, and the strength needed to stand or move. Bones might grow longer and lighter, and muscles in the legs and back could weaken over generations. as they are simply not needed. Children raised on Mars might feel heavy and slow if they ever visited Earth, their hearts and spines adapted to a different gravitational rhythm. Even senses and biology could shift. People living beneath domes, in caves, or in low-light environments might see skin color change, adapting to new levels of ultraviolet rays. Their sense of balance might become tuned to the rotational force of a spinning habitat rather than a planet's pull. Over centuries, these differences could grow larger and more permanent, just as human populations adapted differently in Earth's deserts and mountains. The ultimate question is whether descendants across different planets remain one species, or whether they begin to live and look in ways that no longer match where we came from. Space will not just change our technology and our identity, it will quietly, profoundly change us, forging a new definition of what it means to be human. We arrive now at our final contemplation, a concept that underpins the entire reality of space travel and offers the ultimate paradox of orbital life, the truth that the International Space Station and everything in orbit never stops falling. This quiet, continuous descent is the definition of motion in the void. It looks, from our perspective on Earth, as though the International Space Station, ISS, is floating, suspended effortlessly above the planet. But this visible weightlessness is not due to the absence of gravity, rather it is the purest expression of gravity's reach. The ISS is, in fact, falling toward Earth at all times. It remains aloft because it is simultaneously moving forward at a colossal speed, approximately 28,000 kilometers per hour, so fast that as it falls, the curved surface of the Earth continually drops away beneath it. This perfect balance between horizontal velocity and vertical fall creates a perpetual state of freefall, which we define as orbit. Inside the station, astronauts feel weightless precisely because they, and everything around them, are also falling, constantly missing the ground. There is no sense of downward acceleration, only a gentle, ethereal drift that makes objects float and movement effortless. His continuous free fall reveals a deeper truth about space. Gravity is everywhere, a persistent, invisible force even far above the clouds. Orbit is not the absence of gravity, it is the art of falling forever while racing around the world at an incredible speed. To maintain this delicate balance, the space station must periodically fire its booster engines or receive careful pushes from visiting supply spacecraft. Without these small, calculated adjustments, the thin, wispy upper edge of Earth's atmosphere would gradually slow it down, causing its orbit to decay, leading to an eventual fiery return. The constant need for these boosts ensures that the rhythm of the station is one of vigilant maintenance against the slow, steady pull of our home world. This understanding of orbital motion, the perpetual descent, brings us to the final quiet act of the space journey, the return. To escape the constant fall and definitively leave Earth's gravitational embrace, a spacecraft must reach a precise, immense speed known as escape velocity. This speed is the critical threshold that allows an object to break free from the gravitational pull of the planet entirely, sending it hurtling toward the Moon, Mars, or the deep cosmos. Every launch is a calculated battle to achieve this velocity, an explosive act of commitment written in fire and fuel. As we end our gentle voyage through the most relaxing facts about space, we must remember that the universe is not a single silent clock. It is a place of profound physics, where time bends, metals weld without heat, and breathing is a machine we build and protect. We have journeyed through the body's vulnerabilities, seen the blue sunsets of Mars, and heard the constant mechanical hum of our protective bubbles. Out there, beyond the blue air we breathe, is a vastness full of mystery, beauty, and possibility. And though we live under the constant, familiar pull of Earth's gravity, our minds are weightless, forever free to wander. The universe is waiting, not with a roar, but with a silent, profound invitation to discovery. As we leave our quiet journey through the stars, return to the soft comfort of your home. Take a moment to let the wonder settle into your thoughts. We have drifted through silence, crossed the edge of Earth's sky, and imagined futures built on distant worlds. The journey to the cosmos is an exploration of the absolute limits of human endurance and ingenuity. If you enjoyed this peaceful voyage into the unknown, I invite you to like the video, subscribe to the Whispering Scientist channel, or share a thought below. It helps this quiet corner of curiosity find new dreamers, seekers, and sleepy travelers. Together, we can keep exploring the universe, one quiet adventure at a time. But for now, let go, close your eyes, feel the gentle, soft pull of rest, and let the universe fade into stillness. You are safe. You are warm. You are drifting through the stars. Good night.